So for day 42, we'll go over the review. So let me make it bigger on your screen, and then we can talk about it and kind of look at the questions. So question number 1 says, I toss a penny. I need to zoom out just a little bit. There we go. I toss a penny and observe whether it lands heads up or tails up. So does it land on heads or tails? Suppose the penny is fair. That means it's just a regular penny that we have. And the probability of heads is 1/2 or 0.5, and the probability of tails is 1/2 or 0.5. That means that, what?
C.
We have C. If I flip the coin many, many times, the proportion of heads will be approximately 1/2, not necessarily, but close to it. And the proportion will tend to get closer to 1/2 as the number of tosses increases. And that is true. C. Now, it doesn't mean if you flip a coin 10 times, you're not guaranteed to get 5 heads and 5 tails, right? But if you flip a coin 1,000 times, you're going to get a whole lot closer to 50-50. And does anybody know what that rule is called? It's actually a law. It's called a law or something. You may know that. It's called the law of large numbers. And what it means, it's in your textbook too. It's in probability. The law of large numbers says as we do more and more and we sample more and more, we will get closer and closer to the true probability. So it's kind of like when you played that game we did in experiments. If you do something a couple times, you may get a probability, but that even and odds game, but as you do it more and more and more and more and more, you get a bigger sample, it'll get closer and closer to the true probability. And the true probability here is 50% or 1/2. So the more that we flip a coin, the closer and closer it'll get to 50%. Okay? So number 2, when 2 coins are tossed, the probability of getting 2 heads is 0.25. This means that what? In the long run, 2 heads will occur on 25% of all tosses. Well, let's look at A. Out of 100 tosses, exactly 25 will have 2 heads. That's wrong. No, because we don't know for sure. Exactly 25 we should have around 25 heads. Doesn't mean exactly. The odds against 2 heads are 4-1. Should be 3-1 because it'd be 75% to 25%. That's 3-1. In the long run, the average number of heads is 25%. Is that right? In the long run, the average number of heads is 50%. Yeah. So that was kind of tricky. In the long run, 2 heads will occur on 25% of all tosses. When you do 2, so that is true. It's D. Yes. It sounds a little different.
It doesn't sound
Yeah. I think maybe in the long run, when you're flipping 2 coins at a time, you get heads 25% of the time. But again, and then E says if you get 2 heads on each of the first 5 tosses of the coins, you're unlikely to get heads the 4th time. What that means is, or the next time, what that means is like you're due, which is not true because these are independent events. So like you can't say, oh, it landed on heads 3 times in a row, I'm due for it to land on tails. Eventually it will land on tails, but every time you do it is independent of the last time. So it does not make a difference. Your result in the last time of what you got the last time doesn't make a difference. So number 3, you want to use a simulation to estimate the probability of it getting exactly 1 head and 1 tail in 2 tosses of a fair coin. You assign the digits 0 through 4 to heads and 5 through 9 to tails. Using the following random digits to execute as many simulations as possible, what is your estimate of the probability? So we're simulating the probability of getting exactly 1 head and 1 tail in 2 tosses. Okay, so here's 2, here's 2, here's 2. So first of all, we have 20 numbers, right? So there's 10 trials. So I know it's B, C, or D. So how many times do I get 1 head and 1 tail? So in the first one, I got what?
19 and 26. No, 1 and 9.
1 and 9.
So it's heads and tails.
Heads and tails, yes. Then this one would be
No.
heads, heads. This one would be
Tails,
tails, tails. This one would be
tails, tails. No. Yeah, tails, head.
tails, heads. So now we've had 2, right? Because 19 was 1 head and 1 tails, and 50 was 1 head and 1 tails. What about 34? 34 means you're getting 2 heads. 05, heads, tails. So now we've had 3. 75,
No.
no. 60,
Yes.
yes. Now we've had 4. 71,
Yes.
yes. Now we've had 5. 1, 8,
Yes.
yes. Now we've had 6. So we had 6 out of 10. Now, the real probability is 50%. But in our simulation, we got 6 out of 10. Now, if we would have made our simulation farther, it would have got closer to 50%. So that just shows in a simulation, you can get whatever you want. This also shows that how they can make a problem, make you do a simulation where everybody has to do it the same and you have to get the same answer. So that's kind of showing how a simulation would work. If they want you to go to a specific number line in the table of random digits, they'll put that in the problem. And so that's kind of what they did there. So if you go 2 at a time, 6 out of 10 times you would get 1 heads and 1 tails, which is D. Number 4, the collection of all possible outcomes of a random phenomenon is called a what? It is a sample space. Okay. Remember, census is in our last chapter. Census was when you take all. That's when you sample everybody, the whole population or the whole school, whatever you want to do. And the census is what's going on now that they're doing for the country. Oh, they're still doing it, but they're wrapping up part of it, yes. Number 5, an assignment of probabilities must obey which of the following? Okay, so think about it. A, does the probability of any event have to be between 0 and 1?
Yes.
Yes.
What does inclusive mean?
B, inclusive means it could include 0 or 1. And it could. 0 means it never happens. 1 means it always happens, right? B, does the sum of all the probabilities have to add up to 1?
Yes.
Yes. So we've got A and B already, so it could be E, right? C, the probability of an event is the sum of the probabilities of outcomes in the sample space in which the event occurs.
No. I don't even know what that said. No. It doesn't make sense at all.
Okay, says, all right, let's say the sample space is rolling a die. So you would have 1, 2, 3, 4, 5, 6, right?
Yeah.
Okay. Then each one would have a probability of 1/6. Okay. Now, if I said the event was rolling an even number, you could find the probability by adding up the probabilities of outcomes in the sample space where the event occurs. So I could add up the 2, 4, and 6, and that would give me 1/6 plus 1/6 plus 1/6, which is 3/6, which is 1/2. So there is a way. Like if I say, if there's like a bunch of things up there and we want to know the chance that it happens, we can just add them together, the different probabilities. So it is D. All 3 can work. But C, yes, was a little bit confusing on how they worded it. Number 6, event A has a probability of 0.4. Event B has a probability of 0.5. If they are independent, then the probability that both events occur is. If they're independent, what does that mean you can do? You can multiply them. So 0.4 times 0.5 is, all right. So there's number 6. Number 7. If you draw an M&M candy at random from a bag of the candies, the candy you draw will have one of 6 colors: brown, red, yellow, green, orange, tan.
Ew.
It's disgusting.
The table below, just go with it. I thought blue was on there, but anyways, the table below gives the probability that a randomly chosen M&M had each color before blue replaced tan in 1995. That was when I was 8. So I was eating some tan M&Ms when I was younger. Yeah, I didn't know that though. Did you know that? Okay. Well, of course you were like. Now, the probability that you do not draw a red, first of all, what probability goes in for yellow? 0.2, because the other ones add up to 0.8. So yellow is 0.2. So the probability that you do not draw a red candy is, you could add up all the other ones, or you could do what? Subtract 0.2, right? So 1 minus 0.2. So that is 0.8. All right, that's the And I will tell you, it is hardly ever this on a stats question, because if they're going to give you a question, they should allow you to actually calculate it. Otherwise, we're not assessing your statistical ability. So a lot of times they just throw that in there just for people that don't know what they're doing. That's typically correct. Number 8, using the table from problem number 7, what's the probability that you either draw a brown or a green? Yep. And those are what type of events would we call those?
Independent.
They're not independent.
Oh no, they're what's the word?
What type of
Oh, it's
events?
disjoint.
Disjoint or mutually exclusive.
Oh,
So you can't draw a brown and a green at the same time. That means they are disjoint or mutually exclusive events, which means when you want to find the probability of one or the other happening, you can just add them together. And that is how you do number 8. Okay, number 9. Suppose A and B are independent events with the probability of A being 0.2 and the probability of B being 0.4. What is the probability of A and not B?
0.12. Right?
How would you get that?
Because the probability of not B is 0.6. Because it's the opposite.
Okay.
Or not the opposite, but it just
Yeah,
comes out to
the
1.
complement of it.
And then 0.6 times 0.2 is 0.12.
Okay, so if we know the probability of B is 40%, then the probability of not B would be 60%. And you have 20% times 60%, and that would give you 0.12. That's your explanation. There it is. So number 10, suppose we roll 2 6-sided dice, one red and one green. Let A be the event that the number of spots showing on the red die is 3 or less, and B is the event that the number of spots showing on the green die is 3 or more. The events A and B are, let's think about it. Are they disjoint events? Can they happen at the same time?
Yes.
Yes, so they're not disjoint, so you can mark that away. Disjoint means they can't happen at the same time. Are they conditional events? No. There's no extra information given there. Are they independent events?
Yes.
They are, because if the red die lands on a 3 or less, that doesn't change the probability of the green die landing on a 3 or more. It makes no difference, right? Are they what's called reciprocals?
We haven't talked about
No, we haven't.
That's like a whole other thing.
So that's probably not an answer. That's good. And then it says, are they complementary? Well, you can think about it. Complementary means they would have to, if one's 40%, the other would be 60%, right? They would have to add up to 1. So if you're even confused that they might be complementary, think about the red. What's the probability the red lands on 3 or less?
50%.
Yeah, 3 out of 6. What's the probability the green lands on 3 or more?
50%.
No.
Oh no, it's 4 out of
It's 4 out of 6. So 3 out of 6 and 4 out of 6 is actually 7 out of 6. There's no way they're complementary events. So that wouldn't make sense anyway. Okay? Because they overlap. Complementary events don't overlap. Right? Because if they're complementary, it either rains or it doesn't rain. 3 or less and then 3 or more, they overlap at 3. The number 3.
So like that would be in the middle of your Venn diagram. Would be
Yes.
3.
Yep. Number 11. A system has 2 components that operate in parallel as shown in the diagram below. Because the components operate parallel, at least one of the components must function properly if the system is going to function properly. Let F denote the event that component 1 fails, and G is the event that component 2 fails. Suppose F is 0.2 and G is 0.03, and they are independent. So basically, you are here to explain all that. You are, let's say, this is plugging your computer into the wall. There's 2 things that have to happen for your computer to turn on. That's basically what we're saying. So the outlet could fail or your charger could fail. We'll say that. Those are the two. I mean, you can think about this as just you can make it into any problem you want. So two things have to happen for us to get a good result. There's a 0.2 chance that the first one fails, and there's a 0.03 chance that the other one fails. But we need them both to work for this to work. So the event corresponding to the system failing during one period of operation is. I mean, what would be if we need to know the probability of the event failing? That would be the probability of what? What does F and G stand for? It stands for it fails, right? So how many of them have to fail for it to fail? Only one has to fail. Because if one fails during one period of operation, the thing's not going to work. Like if your charger fails, it's not going to turn on. If the outlet fails, it's not going to turn on. So only one of them have to fail. So how do we find the probability of only one of them failing? That's the probability of F or G. Because only one of them have to fail. F could fail, G could fail, or they both could fail, right? That's the probability of F or G. F and G would mean they both fail. That doesn't have to happen. Not F and not G means one of them. Yeah, right. And that's what we're doing. So that's what we would try to find. What's the probability of F or G? That means the first one fails or the second one fails. Because if either one of them fail, then it's not going to matter. The thing's not going to work. Now, event A occurs with a probability of 0.8. The conditional probability that event B occurs given A is 0.5. The probability that they both occur. So what I want to give you here is there is an AP Stats that we talked about formula sheet. This is on the formula sheet. So on the formula sheet, it gives you this probability. The probability of A given B. Equals the probability of A and B over the probability of B. So it gives you this formula. So you'll have that formula for the test. Now, in this problem specifically, it says the probability that both event A occurs with the probability. So we want to do this. We actually want to do this one backwards from what they give you. This is the formula they give you on the exam. But on this, we know the probability that event A occurs. Okay? So, I'm going to change it around. Because we know event A occurs. So we're given, the piece of information we're given is that event A occurs. All right? So we're trying to find, so notice what we're trying to find. We're going to be given two of these three things. They're always going to give you two of the three pieces. So the probability of B given A, if you're given A, you're always dividing by A. Because what you're given is your denominator. Is the probability of A and B over the probability of A. If it was the other way around, probability of A given B is the probability of A and B over the probability of B. Because B would be what you're given. So let's look at this. Event A occurs with the probability of 0.8. The conditional probability that event B occurs, given that A occurs, is 0.5. So the probability that event B happens, given that A has happened, is 0.5. So this is 0.5. And we also know the probability of what? What did they tell us in the very beginning?
Event A
is 0.8. So we know two of the three in the formula. So, to find the probability that both A and B occur, what should we do?
Multiply by 0.8.
Algebra, yeah. Multiply by 0.8. It's like saying x over this equals this. So times 0.8. So, the probability of A and B occurring is 0.8 times 0.5, and we know 8 times 5 is 40.
Okay,
So that's
like,
0.4.
what was the point of all that confusing, like that, I had it right, and then I thought I was wrong because we did all the formula stuff, and then I was right.
That is the formula.
Like, why?
That you're given goes on the bottom. So that's how I knew that the probability A went on the bottom, because we were given that A occurs in this problem. All right, so we move to, those are conditional probabilities. They are some of the harder ones. So you move to 13. The probability of a randomly selected adult having a rare disease for which a diagnostic test has been developed is 0.001. So let's think about it. So here's the adult. So the probability of them having a rare disease is 0.001. So what's the chance of them not having the rare disease? Point
0.999.
Yes. Okay. Now, the diagnostic test, so the test they use to pick up whether the person has the disease or not, is not perfect. So the probability the test will be positive is 0.99 for a person that has the disease. So if they have the disease, the chance that it says they have it, that it's a positive result, is 0.99. So what's the chance that they have that it says a negative result? 0.01. 1% of the time, right? So 99% of the time it'll say they have the disease, which is what it should say because they do. But 1% of the time they'll get that false negative, right? It'll say they don't have the disease when they really do. Now, for a person with the disease, it says so the probability the test will be positive is 0.99 for a person with the disease and 0.02 for a person without it. So for a person without the disease, the test is still going to say that they're positive 2% of the time, even when they're not. And it's going to say they're negative 98% of the time. And this does happen sometimes with different things. That's why sometimes if there's diseases or rare things that people have, they will get a second opinion or test it twice or 3 times just to make sure that it actually is what it is, because it could have just had a bad reading that one time. Okay, so the proportion of adults for which the test would be positive is. So if we need to find, if you have a rare disease and you test positive, we need to multiply those together. So how many have a rare disease and test positive?
0.00099.
Is that what it was? 0.00099. Okay. And how many, it says the proportion of adults where the test will be positive. How many do not have a rare disease but they still test positive? So 0.999 times 0.02.
0.01998.
Now, those are the only 2 ways that somebody can be positive, right? They can have the disease and test positive. They cannot have the disease and test positive. Those are the only 2 ways. The other 2 branches that you would multiply are ways they could test negative, and we don't need those. We need the proportion of adults where the test will be positive. So we're going to add these 2 together, and you're going to get what?
D. 0.02097.
Yes. So adding 0.00099 and 0.01998 gives you 0.02097. So basically what happens is a little bit more than 2% of the time, about 2.1%, people are going to test positive for this, and the rest of the time people are going to test negative for this. And we knew it would be close to 2%, right? Because most people don't have the disease and 2% test positive. This is a very small number. The worst thing that can happen in this case is what? What's the worst scenario?
False negative.
Yeah. So if you have the disease, No, that's not the worst, because then